In the last module, we saw some examples of LTL formulae and their corresponding Bucci automata. In this module, we will provide the first steps towards the algorithm for converting any LTL formula to a non-deterministic Bucci automaton. For this task, the first step would be to understand the evaluation of an LTL formula on an infinite word. Let's see some examples. Suppose P1 until P2 is an LTL formula. Consider this infinite word over the atomic propositions P1, P2. P1 until P2 is an LTL formula made out of the subformulae P1, P2, and P1 until P2 is again a subformula which is equivalent to this formula itself. Let us now try to evaluate each of these over this word. P1 and P2, it's simple. At any position, find whether P1 is present. If so, then the entry here would be 1. Otherwise, it will be 0. So in this word, the first letter is P1, so P1 is true here. P2 is not present in the first letter, so it's 0 here. Similarly, here P1 is 1, P2 is 0 as P2 is not present. Similarly, here and here, P1 is 1 and P2 is 0. Here P1 is 0 and P2 is 1. Here P1 is 1, P2 0, P1 is 1, P2 0. Here both P1 and P2 are 1. Given this word, you can evaluate P1 and P2 on this at every position and fill in these cells. What about P1 until P2? Look at this position. At this position is P1 until P2 true. P1 is true till P2 becomes true. So at this position it is true. Similarly, here also it is true. Here, here and here it is true. Similarly, at this position, P1 until P2 is true. So all over the place, P1 until P2 is true till this position. We have not considered the rest of the word. Let us do the same on some other word. Here P2 never occurs. So the entry corresponding to P2 is always 0. P1 is 1 here. 0, 1, 0, 1, 0, 1 and so on. What about P1 until P2? Since P2 never becomes 1, P1 until P2 would always be 0. At this position, P1 until P2 is 0. At this position, P1 until P2 is 0 and so on. At every position, P1 until P2 is 0. Doing this evaluation gives us an infinite table where each entry corresponds to the evaluation of the subformula at that particular position. Let us look at the formula GFP1. Recall that f of phi can be written as true until phi and g of phi, that is always phi, is not of true until not phi. It is not the case that f of not phi is true. So this is not of true until not phi. Let us now rewrite GFP1 in terms of these two equivalent formulas. So change FP1 to true until P1. This is G phi, where phi is FP1. So G of true until P1 becomes not of true until P1. Okay. Now what are the subformulae of this formula? Before that, consider the word. Some word, we want to evaluate this formula on this word. So we need to look at the subformulae of this formula. They are P1 true, true until P1, not of true until P1, then true until not of true until P1, this one, and then finally the entire formula itself, not of this entire thing. Let us now evaluate each of these subformulae on this word. What about P1? Here it is 0, 0, here it is 1, here it is 0, 0, 1, 0, 0, 1 and so on. True is always 1. True until P1. P1 is true here. Until that point true is true. So here true until P1 is 1. Here true until P1 is 1. Here true until P1 is 1 because P1 is present. In fact, till here true until P1 is 1. Because from every position here you can reach a position where P1 is true. What about not of this? If this is 1, this will be 0. So you need to flip this row. What about true until this formula? This formula is never true. So true until this formula will be 0. And this is not of this entire thing. So you need to flip this row. That will give us 1. This cell, the one corresponding to the last row and the first column, this will tell whether this word satisfies the formula or not. If you remember the semantics of LTL, we evaluated this formula on this position. It says that it is 1. So GFP1 is satisfied by this word. So this word had P1 coming periodically and hence P1 comes infinitely often. Let's look at another word where you have P1, P1 and then always the empty letter. Evaluating P1 gives us 1 and 1 here and everywhere else it's 0. True is always 1. What about true until P1? It is true here, it is true here and here it is 0. Because here P1 is true, here P1 is true and here you never reach P1, assuming that this is how the entire word is. So it's going to be 0 all over the place. Not of true until P1 will be the flipping of this row. So it is 0, 0 and then 1, 1, 1, 1, 1. Now what about true until not of true until P1? It is true until a point where there is 1 here. So here all over the place there is 1. So true until this formula will be 1 always and not of that will be 0. Look at this entry. This entry says that this word does not satisfy GFP1. Clearly P1 occurs only twice and after that it never occurs. This table explicitly shows the evaluation of this formula on this word. Let us see one last example of this evaluation on a slightly complicated formula. Recall that f of phi is true until phi. Let us rewrite f using until. You will get true until this entire thing. What are the subformulae? Before that, let us consider some word. What are the subformulae? P1, P2, not of P1 and not of P2, not P2 until P1, X of not P2 until P1, then this and not P1 and X of not P2 until P1, and this entire thing true until that. True is also just the formula. True is a subformula. However, since true is always 1, I have not written it explicitly. Let us now patiently evaluate the subformulae on this word. For P1 and P2 it is simple. Here both of them are 0. Here P1 is 1, P2 is 0. Here both of them are 0. Here both of them are 0. Here P1 is 1 and P2 is 0. Here both are 1, both are 1. Not of P1 is going to be the flipping of this row. Not of P2 is the flipping of this row. So 0, 0, 0, 0, 1, 1, 1. That becomes 1, 1, 1, 1, 0, 0, 0. Similarly here 0, 1, 0, 0, 0, 1, 1 becomes 1, 0, 1, 1, 1, 0, 0. What about not P2 until P1? Firstly, since P1 is true here, not P2 until P1 will definitely be true in these entries, in these positions. Look at this position. Since not P2 is 1 here, not P2 until P1 is true here. Similarly, not P2 is true here, so not P2 until P1 is true in these two cells. What about this cell, this position? Here P2 is true, so not P2 is false. Hence, not P2 until P1 should be 0 here. Similarly, here, since P1 is false, you need to check if not P2 is true till the first position where P1 is reached. However, here already not P2 is false, so here not P2 until P1 will be 0. Let me repeat. Here not P2 is false, so you get 0. Similarly, here even if not P2 is 1, here not P2 is false, so you get 0 here. What about X of not P2 until P1? To evaluate this, you need to see this one. You need to check what is the value of not P2 until P1 in the next position. Hence, it is going to be 0 here because it is 0 here. Here it will be 1. Here it will be 1. You just look at the immediate diagonal towards the top. So here it is 1, 1. Here it is 1, 1. Here it is 1. Here it will be 1. Now what about this position? We do not know the value of not P2 until P1 here. So this could be either 0 or 1. Let us just assume that it is 0. We have not given what happens to the rest of the word. So with this incomplete information here, you just assume that it is 0. This entry is going to be the AND of this entry and not P1. So what it is going to be here, it is 0 here, so it will be 0. Here it is 1 and 1, 1. Here it is 1 and 1, 1. Here again it is 1 and 1, 1. Here it is 1 and 0, 0. 1 and 0, 0. 0 and 0, 0. This is going to be true until this. As long as you can reach 1 from this position, then this is going to be 1 here. So this formula is true here, here and here. So up to this position at least we know that this formula is true. What about here? We do not know the value of this row beyond this position. So we cannot confirm what the values here would be. Suppose the rest of the word was just P1, P2, P1, P2, P1, P2. So always P1 is true, so not P1 will never be true and hence this entry will always be 0. In that case, this will be 0 as well. Okay. So this infinite table is giving us the evaluation of this formula on this word. So far, what we have seen is, given an LTL formula and given a word, we can form this table which evaluates each of the subformulae at every position of the word. We have seen these examples. These tables will be called formula expansions. For example, for the formula P1 until P2, these are P1 until P2 expansions. For this word, this is the P1 until P2 expansion. For this word, this is the P1 until P2 expansion. For this word, this table is the not of true until P1 expansion and so on. We are just giving these tables a name. We are calling them formula expansions. The key idea for converting an LTL formula to an automaton would be to look at these columns as states. You see that the number of columns is finite and each column can take either 0 or 1. So the number of column vectors that occur in this infinite table would be finite, firstly. Our goal is to look at these as states. So the first state would be this column vector. After reading P2, then it will go to this column vector. Then reading this, it goes to this column vector and so on. This idea will be explained in more detail in the next module. However, since this is the goal, it is important to understand these formula expansions better. This is what we will do in this module. Understand certain properties of these formula expansions. Let us see what these properties are. Firstly, every expansion satisfies a word compatibility property. That means if the letter does not contain P1 and P2, then it will be 0, 0. If it contains P1, then the entry here will be 1 and the entry here will be 0. This is by definition of the expansion, this property will be satisfied. If P2 is this letter, then it will be 0 here and 1 here. Similarly, if P1, P2 is the letter, then it will be 1 in both these entries. So this is what we have seen here. The first two rows correspond to the word. It's compatible with the word. The first two columns are compatible with the word. So here first two because P1 and P2, here just the first one because only P1. The atomic propositions, the subformulae corresponding to the atomic propositions are compatible with the word. Now, AND-NOT compatibility. Suppose phi is a subformula and not phi is another subformula, then in the expansion, if the entry corresponding to phi is 0, then in the same column, the not phi should be 1. Similarly, if phi is 1, then not phi will be 0. Look at this. P1 was 0 means not P1 will be 1. Again, P2 is 0 here means not P2 will be 1. Similar. So you see there are many not formulas. If true until P1 is 1 here, the not of that will be 0. So if you have a formula corresponding to phi and not of that, the row corresponding to the not will be the flipping of the phi. Similarly, if you have phi 1, phi 2 and then phi 1 and phi 2, then this is how the expansion would look like. If the entry corresponding to phi 1 and phi 2 are 1, then the entry corresponding to phi 1 and phi 2 will be 1. If it is 0, 1, it will be 0. If it is 1, 0, 0, if it is 0, 0, it will be 0. You can check the example there. This property is called AND-NOT compatibility of the formula expansion. One more property is the X-compatibility. If phi is 0 here, then x phi would be 0 here. In the sense, in every entry of x phi, you look at the next position and look at phi in that next position. This will be equal to that. So if this entry is 1, then you look at the next position and go to phi there. This equals that. We have seen this in the previous example as well. The next important thing is the until compatibility. Suppose you have phi 1, phi 2 and phi 1 until phi 2. If phi 1 until phi 2 is 1, then either phi 2 is 1, in which case you don't care about what phi 1 is. So if this is 1 and phi2 is 1, then this could be either 0 or 1. If this is 1 and this is 0, then definitely phi1 should be 1 and phi1 until phi2 should be 1 in the next step. This is very important here. If phi1 until phi2 is 1 here and phi2 is 0, that means phi2 is yet to be seen. So phi1 has to be true and later phi2 has to be true. So that means in the next immediate step, phi1 until phi2 will definitely be true. Let us have a look at one of the expansions. Look at P1 until P2 here. If this is 1 here, this is 0 here, then definitely this will be 1 and this will be 1. Now, suppose phi1 until phi2 is 0, then this entry should definitely be 0. Moreover, what about this entry? This could be either 0 or 1. If it is 0, we are done. So you can have 0, 0, 0. Or if this is 1 here, then this has to be 0. Okay? If this one and this one are 1, then this would have been 1 corresponding to this pattern. If this is 0 and this is 1 here, then this has to be 0. Okay, let us have a look and see. Look at this position. This is 0 here and this is 1 here. Then here it has to be 0. Okay. It just says that if P1 until P2 is false and currently P1 is true, then in the next step, definitely P1 until P2 should be false. Because if this was 1 here, this means that from this position P1 until P2 is true, then since P1 is true here, this would have also been 1. Okay. So these are the patterns that are possible for until. This property says that you look at the formula expansion and you look at the rows corresponding to this until formula, to some until formula, then it has to look like this. Okay. Now, there is one more condition to this until compatibility. This is telling some kind of a local pattern. Let's try to see what happens. This is a possible pattern for until, right? This is possible, 1, 0, 1, 1. Similarly, again, 1, 0, 1, 1, it's possible. And it can go on and on. What does this say? This says that P1 is phi1 is always true. Phi1 until phi2 is always true. However, phi2 never becomes true. This is clearly wrong. So we need to add one more condition to this until compatibility. Eventually, phi2 will become true. It cannot happen forever that phi1 is true, phi1 until phi2 is true, but phi2 is always 0. This particular pattern cannot keep occurring forever. This definitely happens in the formula expansion. Let's look at an expansion and see. See here 101, 101, 101, 101, and then you have 1, 1. Okay. If this is 1 and this is 1, sometime you will have P2 to be 1. This is the eventuality criterion. So we have seen word compatibility, which is easy, not and compatibility. Again, you look at the phi's, phi1, phi2, then phi1 and phi2 will be just the and of them. X-compatibility, and then the until compatibility. Until compatibility was this one. you look at the entries have to look like this, and then we have this eventuality condition. These are the properties satisfied by expansions. One more property satisfied by expansions of words that belong to the language is that you look at the first column, last row. This entry corresponds to this full formula that will be 1. For example, in this word, P1 until P2 was true. So this entry corresponds to 1. In this word, P1 until P2 was false. So this entry will give you 0. Similarly here, this was GFP1. This word satisfies GFP1. Hence, this entry would be 1. This word does not satisfy GFP1. Hence, this entry would be 0. Similarly, this word satisfies the formula. Hence, this entry would be 1. Expansions where there is a 1 in this entry will be called accepting expansions. These are corresponding to the words that are in the language, rather the words that satisfy this formula. In this module, we have provided some first steps towards understanding the conversion from LTL to NBA. We saw what are formula expansions. These are simple things. You look at the formula, you look at the word, and consider all the subformulae of this formula and evaluate them on the word. Our goal is to use these columns as states of an automaton. Before doing that, we wanted to understand certain properties of these expansions. We gain some compatibility properties, word compatibility, AND-NOT compatibility, and any expansion has the X-compatibility, and any expansion will have the until compatibility, and also the until eventuality criterion will be satisfied, and all accepting expansions will have 1 in the last row of the first column. Please try to understand these properties. These properties will be helpful in constructing the states and transitions of the automaton corresponding to the LTL formula.